Hey, it's Kamilescu and welcome again to Mixers Inside. This is a second video about PCB design. The more beginner-friendly approach and a sort of crash course is on my previous video in making of a DJ mixer series. I showed there how to approach PCB design, how to use KiCad software and how to design a simple PCB with summing amp. On this episode, I invited a guest, Professor Eric Bogatin. This is just the smartest person I could imagine I can invite to this channel. So I'm really proud and excited that he accepted my invitation. With Eric Bogatin, we'll talk about PCB design in audio context. Mainly it will be about grounding, because this is where a lot of confusion comes from, and this is where most problems arise from, because due to bad grounding you can get into some problems with catching interference, and basically with proper grounding you can lower the noise of your circuits. And the most fundamental concept that is to be understood to make a proper audio PCB is to treat grounds as a signal return paths, and this is what we will also talk about with Eric. So yes, to tell something more about Eric, Eric is a full-time professor at university, and also he's author of many books about signal integrity, PCB design and such stuff. He's an educator, he conducts many seminars, and also he in this video during our talk he gave a special promo code to check his seminars. It's a free access for 3 months, so be cautious, and the code will be given during our talk. And before I will show you our talk with Eric, I want to show you something more about my PCB, my project, my mixer project, because on the previous video I didn't show much. I want to show you the structure of PCB in my mixer. So here you can see the whole enclosure. It's a 4-channel mixer, and here you can see all the PCBs. The mixer is modular, as I mentioned before, so every channel, because there are 1, 2, 3, 4 channels, so every channel is detachable. So when you have something broken in one channel, you can detach it and work on one board. It's very convenient. And today with Eric we'll also talk about proper interfacing the boards with each other, because it's a quite tricky topic. It's not very difficult, but you must take some things into account to connect two boards properly to achieve proper reference grounding and such stuff. So yeah, I don't have much more to say about my project. I just wanted to show you this wonderful 3D render thanks to KiCad software, because when you design stuff in KiCad you can also render it to 3D, and as you can see, when rendering I can just align the boards with each other and then put enclosure and check if everything is properly aligned without even manufacturing the stuff. So this is very convenient, because you can avoid some mistakes before the manufacturing process. Yeah, so I already said that I have not much more to say, but I said something. So yeah, now it's time to watch my talk with Eric. So I invite you, and I'm really excited to show it to you. Hello Eric, I'm really happy to have you here. Thank you very much for accepting the invitation. Today we'll talk about PCB design and the thing that is really linked with PCB design, the signal integrity. And my guest is Professor Eric Bogatin. And yeah, you already heard me introducing Eric. So let's ask some questions.
Great. So, thank you for having me here today.
Yeah, so first question, first topic I want to highlight is for beginners. I want to say something and also ask you what is essentially PCB design. In my eyes, PCB design is just ability to lay out the components that are already mentioned on the schematic, but the way of placing them together, whether the components should be close to each other or far away, the way of linking them is just an art of PCB design.
Yeah, and I think you've outlined it perfectly here. You have the two steps, the schematic capture and then implementing that as physical design. And I always say the schematic is really a graphical representation of the database. It tells you, here are the components you're going to use, here are the names of the terminals, and when you draw wires, you are creating a net list in the database. And so all it shows is the connectivity of the parts that you're using. It's when you translate those components into the layout like you have here, that's when the signal integrity happens. Because in the schematic, all the signals and the interactions, it's all in the white space. It's not described at all in the schematic. So you're exactly right. It's the layout is where you have to start worrying about the signal integrity and the signal quality.
Yeah, and there is really something to worry about, because actually when we mess up the PCB design, our circuit cannot work properly, right? There are some cases.
Right. Yeah. I always say that the schematic is the absolute best performance you're going to get from those components. When you turn it into the circuit board, all the interconnects are going to do is screw things up. And our job is to try to minimize how much the interconnects screw things up.
Yeah, maybe the best example would be for instance, op-amps that have very high performance, and on the datasheets we can see some crazy low THD numbers and crazy specs, but we must be aware that when we lay out things wrong, we wouldn't get the best out of this, yeah?
Exactly. And sometimes with op-amps, you get feedback if it's high gain and high bandwidth. You get feedback from the output to the input through the interconnects that is not in the schematic. It is in the physical interconnects themselves.
Yeah. So when we highlighted this obvious issue, let's go further. And I want to ask you, because today we are talking mainly about audio PCBs, PCBs that deal with analog audio signals. And I want to ask you what can make audio PCB design special. And nowadays, when we see some boards that are used in various devices, they deal with some digital signals, they deal with signals that are very high speed, and they really require some special taking care of some special stuff, like for example impedance, or as I mentioned before, keeping the components closer to each other or far away. And maybe you can say your views about what makes audio PCB design special, because on first glance it should be pretty easy. We deal only with bandwidth till 20 kilohertz in theory, so the signals are really small, but maybe there is something that we can actually do wrong, yeah?
Yeah, so you're right that audio design is different from high-speed design because I think there are really two physical effects that are related to, surprisingly, electromagnetics. One is where the currents flow in the planes in a circuit board. At above about 100 kilohertz, which is above the audio range for your signals, above 100 kilohertz, the return currents for any signal line is flowing right underneath that signal line in the ground plane. But below 100 kilohertz, those currents spread out. And as they spread out, they have some series resistance in the planes. And even though they're spreading out and they're low frequency, you can still get some IR drop in the planes themselves.
Okay.
And that is a very subtle source of resistive crosstalk at low frequency. So it's not it doesn't scale with frequency. So it's not like inductive or capacitive crosstalk. that both get larger with higher frequency, it's DC or DC to 100 kilohertz. It's IR drop. And so the one of the differences is where do those return currents flow? It's different at audio frequency than at high speed. And I think the other is in your audio signals, you're dealing with really low signals. They're in the millivolt kind of range. And that means that sources of noise that may be common in designs that may be in the millivolt kind of range, now that is going to really degrade your signal's noise. And so you have to pay attention to really small, subtle noise sources in audio design that are still there at high speed design, but your signal levels are so much higher, you don't care about them. And so you have to pay extra attention to those small noise sources.
Yeah. And can you highlight some common mistakes that engineers make during analog audio PCB design? Are there any common mistakes that you just see not every time, but really often?
Well, first I have to say, I don't do a lot of audio design. I do a lot of high-speed design, and so I see a lot of those problems. But in the low frequency and when you have low noise and low noise design, if you have mixed signal, and as a lot of audio systems now have a large amount of digital components to them, you have to keep in mind that the digital signals that are on the same board in vicinity, they could have 1 to 5 volts of signal swing, and the audio signals maybe in the millivolt kind of range. And so we might care about 5% crosstalk in digital signals, but when you have a 1 volt signal that's the aggressor, and you're looking at a millivolt as the signal on the audio line, oh my gosh, that's 1,000 to 1, a tenth of a percent crosstalk between the digital and the analog. That 10%, a tenth of a percent crosstalk now can completely degrade your signal. And so you've got to watch out for the crosstalk from the digital signals that are around, and they're going to create noise on the power rails. They're going to create noise as crosstalk between signals. They're going to create noise because of their return currents in the planes as well. And so you've got to be careful about isolating digital components from the analog components. You got to be careful about keeping the noise from the analog, from the digital signals that generate noise and pollute the power distribution. You got to minimize that noise. And in some cases, if you don't have good, op amps have a power supply rejection ratio. So noise on the power rail doesn't couple directly into the op amp, but it's rejected to, maybe 180 dB, something like that. But when you're looking at millivolts of signals and you have 60 dB power supply rejection, 1 volt of noise is going to give you a millivolt of noise on the op amp. And so making sure that the power line noise supplying the op amps is low is really important. And a lot of times that means filtering from the board level to the op amp or to the amplifier level is really important.
You mean like power supply filtering, yeah?
Power supply filtering, right. 60 hertz is part of it, but with linear supplies or switch mode supplies, it's not so much 60 hertz anymore, but it's the switching frequencies of the switch mode supplies, and it is noise from digital devices that are injecting or causing noise on the power rails. That's what you want to filter out from the analog devices. And that's where good ferrites come in to filter out the noise from the power rail on the board to the analog devices.
Okay, so as I understand, our PCB design is critical to deal with noise and to keep the noise level at
Right.
low levels. So what we can do about it, we can is make zones on the PCB, yeah, like the digital zone and analog zone far away. Try to keep them as not interfering themselves, right?
Right.
But also the thing we should really care about, this is one, I think, of the most misunderstood thing about PCB design is grounding. And I'm really curious about this because I must admit that I don't fully understand this. I have some questions, and I'm really curious if we can deal with if we can lower the noise levels with proper grounding. Probably the answer is yes, because as you said, you gave an example of some RF situation where we have like our aggressor is RF signal that makes some really small voltage drop on a ground line or ground plane, and this is where the noise can come from. Yeah. So my first question about grounding is this classic separation of chassis ground and signal ground. In most of the devices with metal enclosure, we see this separation, and we see it on the schematics, and we see it also on the layout. We see that people are separating the chassis ground, so the ground that is connected directly to the metal chassis, and signal ground, so the ground that is connecting the is our let's say reference plane to the reference plane, or maybe not plane but some reference to other signals. So my first question is, should we even separate those two grounds, and if yes, how can we do it? And after answering this question, I have very interesting real-world example we'll jump into. But yeah, the first really important question is how to deal with separating those grounds, and what is the important thing we should keep in mind, and how we can approach this intuitively.
Right. So ground is a really confusing topic, and part of the reason is because of the words that we use. So there are 5 different kinds of grounds. Each of them are a little different, and you have to pay attention to. The first is earth ground, and that is literally connected into the floor and into the dirt, provides a reference for a whole building. I'm not sure what it is like in Poland. In the US, in house wiring, we have 3 different connections into house wiring. We have the high side, neutral, and then we have earth ground.
Yeah, in Poland it's exactly the same.
Okay, so earth ground is distributed throughout an entire building, and that is literally it's a safety feature predominantly. When you have an instrument or an amplifier or some device that has a metal housing on it, we call that metal housing the chassis. And because it's a big piece of metal, we also call it chassis ground. In most instruments, chassis ground inside the instrument, when you plug the power cable inside the box, the earth ground is connected to chassis ground, and that is an important safety feature as well. So chassis ground is oftentimes connected to earth ground. On the circuit board, we have a node in the schematic that we call ground, which we want to really refer to as circuit ground. That is the point at which we're using as a reference to describe the voltage anywhere else. The challenge is that in the board, when we design the interconnect, we're assuming in the schematic, we're assuming that every node that's labeled as circuit ground is the same voltage. There's no voltage difference. And so when we measure a voltage, when a device senses a voltage between an input and the circuit ground, we're assuming that circuit ground is the same everywhere. When we turn the schematic into the layout, if the physical interconnects of the circuit ground, that ground plane typically, if there is no current in that circuit ground plane, then there's no voltage drop across it. And so every point on that ground plane is going to be the same voltage, and that's a good reference to wherever we're using in the circuit. But if there is current in that ground plane, then we can have IR drop, we can have inductive drop, and that means different locations have different voltages. And so when we use a ground plane in the board, we want to think of it as really two different purposes. One is the DC reference that we're using to compare to every other voltage, and the second is as a return path. And so we want to, it nowhere in the schematic does it say return path. And so when we do the layout, we want to be thinking about where are the return currents flowing, and where possible, maybe use a separate trace as a reference voltage that is assured to not have any current flowing in it. And that effectively is like a differential pair. It's having a signal line and a reference. And if you think about the interconnects from, you know, a microphone, for example, or an input that's a low-level signal, the having the connection between the microphone and the amplifier as the signal is one trace, and the return connection from that microphone ground or the ground reference, another trace that goes to the input of the amplifier, then if there's no current through that trace, there's no voltage drop, and we're seeing at the amplifier the same voltage as at the microphone, for example. If we used a path from the circuit ground of the local ground of the microphone onto the circuit board ground plane, and there was current in that ground plane, and that current is modulated by 60 hertz, or it's modulated by power line noise, or it's modulated by return current noise, then we're going to see that noise at the input of the amplifier on top of the microphone input. And so thinking about the interconnects in terms of reference ground and return current helps to identify where the source of the noise comes from. And I find it very useful in looking at any low-level signal, regardless of where it is. I do a lot of work with biomedical instrumentation, where it's, again, low-level signals that we're looking at. There, differential signaling is really important, because that differential signal is basically the voltage difference at the input of the sensor, and we carry the reference of that sensor all the way back to the amplifier as a differential amplifier. And so thinking about audio signals as differential signals, where the separate interconnect provides the local reference, helps to reduce the sources of noise.
Okay, I see. So we can treat every signal as kind of differential pair, but the problem with single-ended signal is that one of the wire is actually ground, yeah?
Right.
And it can be sensible to modulations from other sources. And,
right.
Can you give some examples how can this ground be modulated? Is it, for example, I don't know, strong current draw from the power supply or something like this?
Yeah, exactly. If there's a digital signal that's switching, if there's an ADC that's got 20 kilohertz reference, and the digital side of the device is pulling current at some high audio frequency range, that return current can be flowing in the ground plane, or if there's a high power amplifier that's drawn a lot of current from the power supply, that return current could be flowing through the ground plane. And typical resistance in the ground plane, that return current, it's about a square or two of resistance, and in 1 ounce copper on a board, that's about half to 1 milliohm, depending on the thickness of the copper. And so there could easily be 1 or 2 milliohms of DC resistance in that return path conductor, that ground conductor, that's the return path. And if you have an amp of current, that's a millivolt. And so you could have a millivolt of noise from one end of your reference to the other end. And if your signal from the microphone is a couple of millivolts, you can see a pretty large amount of noise contributed to it. And that's where you want to minimize the sharing of the reference conductor with the return conductor. And that's why it's important to think in your engineer's mind's eye the difference between a reference conductor and a return conductor.
Yeah, but the thing that confuses me a bit is that in most of the literature I read about PCB design, especially modern literature, because back in the days people used to extensively say about splitting grounds, especially analog and digital grounds, to make the split, to keep them separate, to keep them just not bond together. And now modern literature basically mainly on the point of view on EMI terms and interference, literature says that the solid ground plane is always the best solution because it provides you very low impedance. As you said, the ground plane is just a piece of copper that has a very potentially the voltage drops during interference will be kept low because of the low impedance, right? But from the empirical perspective, for example, it's a real-world example. A couple of years ago, I designed a phono preamp, and this phono preamp is something very sensitive. There are some signals flowing in the millivolt range, and at the same time, I decided to power this phono preamp with a power supply based on voltage doubler. And this power supply with a voltage doubler caused some really serious currents charging the capacitors. And I noticed that when I used solid ground plane and components were pretty close to each other, but the signal section was physically separated from the power supply, but they shared the same ground plane, I had some problems with interference. And then when I separated it somehow and made a cut and really like a power supply zone and signal zone, I started to notice that the interference is lower. So I somehow broke the rules. Yeah, I didn't go with a solid ground plane, but it actually helped me. And this is my confusion.
Great. Perfect example. And you're right. In general, the recommendation is never split a ground plane because of the potential problem of if any signals cross the split plane, that introduces a huge amount of noise. And so generally, in most designs, there is never a need to split a ground plane, and there are potential problems that can arise if the ground plane is split. But there is that one exception, and that's the exception you identified. In fact, this topic of when do you split a ground plane is something I'm actually doing a webinar on June 12th. So I do, one of the hats that I wear, in addition to Rule Number 9 hat, is I'm a fellow with Teledyne LaCroix, and I do periodic webinars with Teledyne LaCroix. And I'm gonna make you and your viewers an offer here. So on the so many years ago, I used to go around and I used to do live courses on signal integrity. We recorded them all, we put them on a website, and it is now the Signal Integrity Academy. And it's my company was acquired by Teledyne LaCroix, and so Teledyne LaCroix now hosts the Signal Integrity Academy. And so I've got more than 200 hours of recorded videos on signal integrity courses. And I do webinars with Teledyne LaCroix periodically about best design and best measurement practices. And normally the accessing all the content on Signal Integrity Academy is through a subscription, but I'm going to give you and your readers a special promo code so you all can get it for free. Nice. So if you you can put this in your show notes. So the promo code is EBQ225.
All with capital letters, right?
Case insensitive, doesn't matter. Okay.
Thank you very much. I appreciate it, really.
And so all you have to do is you go to signalintegrityacademy.com. It takes you to the registration page. You can see the example of what's there. Goes to the registration page. Simple, couple page to fill out. And on the second page, it asks, do you have a promo code? And you can type in EBQ225, and you'll get a 3-month free subscription. Nothing else required to do that. And if you go there, you'll see a lot of my webinars and a lot of my courses and webinars on signal integrity that you can view. And this question about when do you split ground planes? What are the pluses and minuses of doing that? I'm actually doing a webinar on exactly that topic on June 12th. And so if any of your viewers go to the Signal Integrity Academy, you can sign up to see that webinar live or view the recording of it. And the example that I show is, I showed an example of generating the crosstalk, this resistive IR crosstalk, when that conductor that we call circuit ground is also used for return current. So it's being used for two different separate purposes. If that return current generates, generates a resistive voltage drop, and you modulate that current because the power rail has noise on it, modulates the current. The signal line that uses that same interconnect for ground reference sees that voltage noise in it, and it's on top of the signal. And that's exactly what you saw. Yeah. You got current from the power line. And I show an example of that. And then I show an example of, okay, there are two fixes. Fix one is, I'm going to separate the returns that are used by the power rail and as the ground reference for my sensitive sensor. In the example I show, I use a little temperature sensors on the board. And if you separate those so that you don't have the return current in the same ground conductor as used to send the signal, you don't have that resistive noise. You don't have the IR drop noise. Perfectly fine way of doing it. Another way of reducing that noise is we use a separate conductor for the reference of the sensor. It's like treating as a differential pair. It's like, even though they're both connected to the ground node, so in the schematic, you don't see a difference. You have to know when you do the layout, I'm going to have a separate trace that goes from the phono jack or the microphone input to the amplifier. Even though it's connected to node 0 or the local ground in the schematic, it's a separate wire that's going from the sensor to the amplifier. And at the amplifier, you can connect that node 0. You can connect it to the circuit board ground because there's no current that's going to flow through that. There's no voltage drop in it, but it's still connected to the local circuit board ground. There's in different layout tools, it's sometimes difficult to separate out that net that you want as the very isolated reference, to separate that from the circuit ground that's node 0 on the board. And so one of the tricks that I sometimes do is I will use a 0 ohm resistor at the amplifier to isolate the trace so it's a separate node. So the net name for that trace is return for sensor 1. Yeah. Because it's connected through a component to local ground at the amplifier. And that way, in the schematic, you can identify, hey, this is a really sensitive reference line that I want a different net than the ground net that's used for all the returns. And even though it's going to be ground, the component that you add is a 0 ohm resistor, and you can just place that 0 ohm resistor on the board. It has no impact on the signal. Or if you know, okay, that's what I'm doing here, you could take it out and just put a short across it and not put the 0 ohm resistor there. But it's a way of tricking the software, the layout software, into thinking about that isolated return that is now protected, so I have no current flowing in it, no voltage drop across it.
Yeah, so basically you're using dedicated wire for one node. It's kind of like splitting the ground. But right. The thing I wondered about is that from EMC perspective, people tell that the best way is to use ground planes. And what happens from the EMC perspective when we use a dedicated wire to make exactly it's connected to the ground node, but it's applied only for one return current, so it can be a wire. It can be shaped not like a plane, but like a single wire.
A trace.
Exactly, a trace. Can this ruin our EMC performance in some cases?
The quick answer is no. because you still have the ground plane in the board that's still providing the low impedance for return currents, but you're using the separate trace as a reference. Typically your amplifier, the preamp or the sensor or the microphone, the currents involved are really small. It's low level voltages, really small currents. And so the resistance of that trace is negligible. It's about, for 6 mil wide lines, it's about 80 milliohms per inch. So, a couple inches long, we're still talking about in the fraction of an ohm series resistance. So it's a negligible amount of resistance. We're not going to drive a lot of current in that line, but we don't have any of the return currents flowing through that will drive crosstalk between some noisy source and the reference. We can do it as a split plane. And in the webinar I'm doing in a couple of weeks, I show an example of exactly that. I show here is a signal line with a wide trace or wide plane underneath it. I have multiple signal lines, parallel signal lines, about an inch apart with a wide plane underneath. And I drive a current through one signal line and its return into the plane. And at high frequency, that return current is directly underneath the signal line. There's no resistive crosstalk. We have capacitive inductive crosstalk between the traces, driven by the dI/dt and the dV/dt, the high frequency changing current and voltage. We have crosstalk, but there's no resistive crosstalk because there's no overlap of the return currents. But in that 100 kilohertz and below frequency, your important audio range, the return currents spread out, and that gives us resistive noise between the signal lines. Even though they're far apart, we still have current flowing under the signal lines. And I show the amount of, it's hard to measure because it's really small, but hey, if you're dealing with millivolt signals, even if you have a couple hundred microvolts of noise, that's going to degrade your signal to noise ratio. And so even though it's really small, for your applications, it can be important. And so I go through the example of measuring it with a scope so we can see how much resistive crosstalk there is between the aggressor line and that poor victim line sitting next to it. And it's measurable with the right techniques. And then I cut, just like you said, I cut the ground plane so that we isolate the DC currents. We still have capacitive coupling, we still have inductive coupling, but at low frequencies, those are really small. But by cutting the ground plane, we isolate the return currents in that ground reference, and the crosstalk goes away. It is below the microvolt range, which I can't measure with the scope. And so that is the only case where splitting ground planes makes sense if you're talking about low-level signals and you have high currents that are using the ground planes.
Yeah.
But the danger you run, the benefit is you cut down and you eliminate that resistive crosstalk. The danger you run is if you're not really careful in how you're laying out the signals so that other signals, your digital signals and even some of the analog signals, don't cross that ground plane. You can, if any of those signals cross the split in the ground plane, you can dramatically increase the crosstalk that you see. And so it's a risk-reward ratio.
Yeah.
If you're going to be really careful, perfectly fine thing to do, but not every layout engineer is really careful. And you have to trace every signal line and make sure it doesn't cross that split. And so that's why I advocate use the solid return, but instead of using the return plane as your reference for low-level signals, treat it like a differential pair and carry the reference with you. And that completely eliminates the risk of a signal crossing the split accidentally. And you still have the benefit of a low current carrying line as the reference, low voltage noise on that line. And so it's really thinking about, changing your mindset, thinking about your low-level signals as differential signals and carrying that differential signal from the source of the sensor, wherever that microphone is, thinking about carrying it all the way back to the preamp so that you have high-level signals on the other side of that preamp and carrying it through a differential pair.
Yes, yes. Thank you very much for covering this topic really deeply, and I would gladly check out the seminars because it's covered even more deeply there, and I'm really curious. But the thing I want to ask still about the same topic is that we talked about treating the ground also as a return path, yeah, for signals. This took a while for me to understand, but I'm already kind of there. But there are some nuances I don't understand still with linked with this split between signal and chassis ground. And I have a very tricky example here on the slide. I don't quite understand. And here we can see the very output of the mixer. This is the output connector. And this is not a differential signal, this is not balanced signal, this is a single-ended one, let's call it, like a reference to the ground. And the very interesting thing is that this output connector uses the sleeve, so the thing that should be connected to ground, it connects the sleeve to the chassis. And I can't really understand the reason behind it, because as we said, we should reference our signals to grounds that are insensitive to interference. Yeah, here the signal is becoming reference to the chassis ground, and this is kind of tricky, and I wonder if you can tell something more about it. What do you suspect is the reason of doing such thing?
Well, probably because it's easy.
Okay.
You have a coax cable that has the signal pin in the center, and the outer shield is the return for that signal. And that shield, the metal housing of the shell on the outside, when you plug it into your instrument, your box, automatically gets connected to the chassis ground. And that by itself isn't the problem. If you think about the voltage coming from the microphone, for example, that there's a sensor there that's generating a small signal. It's a differential signal between the signal and its return.
Yeah.
That return is the coax. And now that goes back to the shell of the jack that gets plugged into the chassis. And so you still have the voltage between the signal and the chassis inside your box. That's your signal. If you pick that off as a differential signal and you connect the signal line back to your preamp and the return connection to the chassis back to your preamp, you still have a very good low-level signal. The low side of the preamp is going to be at the chassis voltage. At the chassis voltage goes up and down, that signal level goes up and down, but that low side goes up and down, but so does the signal go up and down.
Excuse me, but what do you mean by low side?
Right. So in your example here, you have a signal,
yes,
and you have its return. So I call the signal the high side. That's where the higher voltage is. The low side is I hesitate calling it the ground side because we're going to change different grounds. But it's the coax, the shield of the coax. That's the low side. When you plug it into the chassis and you have a wire coming from inside the box, from the signal line, if you now also connect a wire to the chassis at that point, you're going to have two wires, the signal and the low side, the chassis connection. If you connect a preamp and you look at that voltage, perfectly fine. If the chassis voltage goes up and down relative to the outside world, earth ground, both of them are going to go up and down the same. The voltage difference, perfectly fine. Here's where the problem arises. Now your preamp has the two signals, the differential signal coming in, but you're calling the low side circuit ground. And now at your amplifier, if you use a single-ended amplifier, as most of them are, it's got its own local ground reference. And if its local ground reference is a different voltage than the chassis, now that voltage difference between the local ground and the chassis is in series with your signal.
Okay.
And noise between your chassis and local ground is going to cause the noise on top of your signal.
I see.
That's the problem. And so the fix to that, if you're going to do that and have a single-ended plug going into your chassis, from the microphone into the chassis. The fix for that is don't use a single-ended amplifier, use a differential amplifier. And that will subtract off, that will isolate that little bit of voltage noise there may be between the chassis ground and your local ground. And if you have current in the chassis, so you're not supposed to, you should never use the chassis as an intentional return path.
Yes.
But sometimes you get currents in there. If there's any current if there's no current flowing in the chassis, every point on that chassis has the same voltage. There's no voltage drop. The only way you get a voltage drop is current flowing in either inductive or resistive paths. If there's unintentional or intentional current flowing in the chassis, that means different points of the chassis have a different voltage. It's like any return path, you have a different voltage on those return paths. If they're used as references, local references are going to have different voltages, and that's where you get noise injected with the signal. And that's where thinking about the reference path and carrying that along with the signal and making sure you don't have any current in that reference path, that's how you get clean signals without interfering noise.
Yes.
And that means you want to be thinking about using differential amplifiers for your low-level signals until they become high enough so that voltage level is way above any kind of different voltage noise you're going to see in the ground plane.
Yeah, sure. So that's why we often in a high-end audiophile gear we see differential signals. Yeah,
there you go.
This is
exactly.
Just signal is just not a reference to this ground, and there is no potential dirt. Yeah, it's all
Yes.
it goes by its own. Let's say. Yeah.
Yes. Right.
Yeah.
It's reference to the original source, because at that source, whatever that sensor is you're using for the microphone or the pickup, it's guaranteed a differential signal. There's signal and it's returned locally, and that's what you want to carry along with it, so you don't pollute that low side of the signal to the. You don't pollute it with noise from currents from other places.
Yeah, I see. I have some more questions about grounding, but I'm not sure if we covered, if we didn't cover already this stuff. But my other question is about ground splitting. Should we split grounds? And here's then an example where a headphone amplifier on the output jack has its dedicated ground pin, but I believe it's something you already commented on, yeah?
Yes, reference.
Yeah, exactly. So I think this doesn't need any more commenting because we already talked about this. So let's jump to another interesting example, because on many audio mixers we have various channels, and it's extremely convenient to design the mixer in modular way. It makes it really easy to repair, because when one module gets broke down, one channel gets broke down, you don't have to deal with all the boards. You just plug out one board and voila, you work on a small board, and it's much more convenient. But the problem begins when you are thinking about interfacing this module with other stuff you are connecting this module to. And I found in real world two interesting and different examples how signals are getting interfaced, and here we can see the output connectors of channels. And on the first output connector, here on the left, it's from a Rodec mixer. We have various signals, and we have only one common ground pin that is a reference for all the signals. And all the signals flowing, even voltage rails, analog signals, all refer to this one pin. And on the other hand, on the right example, we have this ground interlacing. Every pin has its ground neighbor, let's call it. And what's a better solution in terms of keeping the loops tight and keeping the return paths close to the dedicated signals? What do you think about those two solutions?
Well, I think you just answered that, that the whole idea, and I see these designs are very common. In fact, I use the Arduino microcontroller board for a lot of examples. I teach courses and I use that. And that is a classic example of the worst IOs that you can engineer. Are you familiar with the Arduino? Right? Pardon? Yes, on the left.
Yes.
The Arduino has 13 different digital IOs, and it has one return. And I did a webinar a couple months ago where I used that as the example, and I showed the crosstalk that we get in ribbon cable coming off of that connector. And it's all about, you don't think ground, think return path, like you said, that you want to keep the signal and return close together to minimize the loop inductance and to minimize the magnetic fields that come off of it that couple into other loops. When you have something on the left, then all the returns are flowing through that one pin labeled ground. It's not like ground, it's return. And all the digital signals, their returns flow through there. So you have a lot of crosstalk with the digital signals, and all of the analog signals see that same return path as its reference. Even though it doesn't have much current flowing through it, you have the voltage noise on that return path, and you see a huge amount of crosstalk. And I show in the webinar exactly these two differences, where you have one return and you have 6 IOs that are switching, and you have every other signal or every other connection as a return with the 6 IOs switching. And the crosstalk, due to the interleaving of the grounds, is reduced by almost 2 orders of magnitude over the case on the left. So because of the reduction in the mutual inductance between the paths, you can have a dramatic reduction in the crosstalk. So for audio where you have low-level signals and you're very sensitive to crosstalk, you never want to use a connection like on the left. You want to have interleaved returns. So don't think of it as ground, think of it as return connections. Exactly the same way that we were discussing for the board level, this is at the connector level.
Okay, I see. I will show you one example that may justify the design choice on the left, and I'm really curious what you will say about this. I want to talk about PCB layout of a summing bus. The summing bus that is most popular in mixers is just an inverting configuration with, let's call it virtual ground. Yeah, the inverting output of op-amp due to the non-inverting output that is connected to the ground, the inverting op-amp is still struggling to keep the potential on the ground level, right? And this is a very interesting example of what we were talking about on the beginning of our conversation, that we have that the schematic is just a representation of an idea, and PCB layout is just a way of making this idea real and like placing the components in the real world. So we have this very simple summing bus that have some summing resistors that are connected to this virtual ground node. We can call this node a summing bus, yes? And we have a case here. This is one approach that is also present in the Rodek mixer I showed you, with this common ground return. And we all agree that running signals through this connector, through this kind of connector with one ground pin, is very bad due to crosstalk, because the signals are referenced to the same thing, and the loops are becoming the loop area is becoming significant, and the signals interfere with each other. But what happens if we link those signals via resistors and run it through the summing bus? So the summing bus become at ground potential, yes? I'm not sure if I'm making myself clear, but let's once again analyze this case. And for example, let's take this signal MXL and MXR. So when MXL and MXR are just ordinary normal signals that are referenced to ground, we agree that due to the loops, there is crosstalk going on. But what happens if we plug the signals via summing resistors to those nodes, and those nodes become summing nodes on the ground potential? Does it justify this design choice, and can it prevent this crosstalk we were talking about?
So I don't think there's anything that can justify the single ground connection.
Okay.
Unless everything is differential. And if everything is differential, not so big a problem. The difficulty is that there are two kinds of noise that one of the analog channels is going to see. There is the noise from the digital channels because they're switching and they have current. And by itself, there's going to be a large amount of noise on that. That's the voltage noise between channel 1 and the reference ground connection. There will be a lot of noise on that. In addition, if that ground is used as the reference, so that ground on the connector is different from the ground symbol here on the op-amp. And it's that voltage difference that gives, even if you had no signal coming in on the channels, you're still going to see the noise coming out of the op-amp. And so that voltage difference is the noise that you're going to see. If you used each of the channels as channel 1 is the signal and channel 2 is its reference, then you take the difference between them. There's still going to be noise between channel 1 and the op-amp ground and channel 2 and op-amp ground. There's still going to be noise on that, but the differential, but it's common to both of those. And so if we use channel 1 and channel 2 as the difference signal, that won't see that ground noise. So that's the only case in which you could get around that problem.
Differential approach, yeah?
Differential approach. No matter what you do, if you have a single return, any noise on that ground is going to appear on top of the signals. Your ground point over here, the whole idea is that you have a different voltage on the local ground of the op-amp compared to the ground on the board. If you were to connect a wire between the local ground of the op-amp on the non-inverting input to the ground on the connector, so that it's seeing the local voltage on the return on the board where the connector is, then effectively that's a differential signal. And so you would want to have a separate return conductor, another wire, that is that ground connection, so that the ground wire in the cable is not part of the reference structure here.
Okay.
And it's basically a differential signal. That is what you're trying to do, is make it differential.
So no excuses. It doesn't.
Right.
Doesn't work.
Because you're always going to have a voltage difference across the ground conductor because of not so much the IR drop, but the inductive crosstalk as well.
Yeah, I see. And another question I want to ask you about the summing bus, and it's strictly linked with PCB design and signal integrity, is I showed you this first approach, and it's very convenient because actually when you deal with this long summing bus that is connected to the summing resistors that belong to each channel board, it's really convenient because you don't need much wires. You run one long summing bus connected via resistors, and one wire does all the job. But what happens, and is it potentially better solution in terms of signal integrity? What happens if we actually run separate signals from each channel board to the summing resistors that are really close to the inverting input of op-amp? Because from signal integrity perspective, as far as I know, it's very important, especially when dealing with high-speed op-amps, it's important to keep the inverting node small in area. And when we when we make it longer and when we gather the signal from all the boards, the area becomes significantly larger, and it can be some kind of more prone to interference. Am I right?
So if your traces are controlled impedance, whether you use it for controlled impedance or not, that just means that there's return plane underneath. We can keep the crosstalk low. There is the problem of the, what you're referring to is the fact that the input to the inverting input there's some capacitance in the traces to the ground plane underneath. And so in this case, you have it DC coupled, but if you have it AC coupled, there will be some capacitance between the traces and the return. If you're trying to keep that capacitance low, then keeping the traces short, like you have here, is exactly the right thing to do. If it doesn't matter, if the typical capacitance on a board, roughly about 3 picofarads an inch. So if you have 10 inches is 30 picofarads. If that kind of capacitance between the inverting input and ground, that's not important because you have microfarads of capacitances coupling in and out. If 30 picofarads is not important, it doesn't matter.
Okay.
You want to, in order to evaluate the impact, you want to think about the equivalent circuit model of the interconnect and how it behaves in your circuit. And so the traces are going to be, as long as they're microstrips, so there's controlled impedance, you have a ground plane nearby, crosstalk from other sources is going to be low. There's some input capacitance of those traces you can estimate roughly. And so if you're trying to minimize that capacitance, keeping it short is great. But if that's not important, then whether you have a longer path or shorter path, as long as you don't have interference from other traces nearby, either approach is probably going to give you exactly the same behavior.
I see. Yeah, so this is the moment when I've run out of questions, like theoretical questions. And also because we already, our talk lasts for an hour, and I wanted to ask you if you will be happy to take some time to look at my PCB design and do a small revision, or you think it's just enough and we can just end?
Well, I think you've got enough, and you understand what's going on with the separation of reference and return path. That, I think, is one of the secrets to understanding low noise design. And I think you already understand. I'm happy to look at your design maybe another time.
Okay.
And again, I want to invite you and all of your viewers to check out the Signal Integrity Academy. A lot of these topics, well, of course, we deal in signal integrity with much higher frequency, but a lot of the concepts apply to the low frequency as well, especially this idea of thinking about return path separate from reference. Very important distinction. And unfortunately, we refer to them all as ground, and they're not all the same. And so we want to get in the habit of separating earth ground, chassis ground, reference ground, return path, and local ground. And that way, that'll help us keep straight in our head how the real differential signals are traveling through the interconnects.
Okay. So really, I'm really grateful, and thank you for finding some time to straighten out those issues. I think that there are a lot of materials about the modern PCB design dealing with digital stuff, but not much is highlighted about this stuff we talked about. But I found out thanks to you about those seminars, and I will really gladly participate and also use the code you given. So
very good.
Thank you very much.
It's been a pleasure chatting with you. Hope we chat some more in the future.
Yes. Thank you very much.
Okay, bye-bye.
Thank you very much for watching this video. I hope you learned something. I learned a lot, and I'm looking forward to invite some more experts to discuss very interesting audio-related topics. If you have any ideas, please feel free to let me know in the comments. Thank you once again, and see you next time.